Hello, Algebra 1 students for 2020-2021. This is the third and final installment of your summer math work, and I'm pretty sure that this installment can be one video of moderate length and one worksheet with problems based on this one video. The topic for this installment is a very limited one known as simplifying a root. This is a skill that is mechanical. It does not require a lot of creative thought like word problems do. And it is my hope and expectation that you can perform this skill, accomplish the task of simplifying a root before we get back to school. I think that's reasonable, so let's give it a try. We do need a little background information before we get into the actual skill involved. So let's start with a table of what are known as the perfect squares. In the left column of this table, I have n, which represents the whole numbers, beginning 0, 1, 2, 3, 4, 5, and so on. And I continue over to the right column here and go as far as 15 for the n. And then I skip a few and identify 20, n is 20, n is 30. Then I skip some more and go to n is 100. And in the right column is n squared. So just square whatever the whole number is to get n squared. Now, the numbers in the n squared column are known as the perfect squares. And to understand what that means, there are various ways to understand what that means. But one way is to make this statement. If you take the square root of any of these perfect squares, you get a whole number. So, for example, the square root of 49 is 7. Why? Because 7 squared is 49. And there's a aspect of the notation here that we have to mention. This is the square root symbol here. Kind of looks like a division sign with a little tail on it. And there's a little V in here of the root sign. And when there's no number inside that little V, it is assumed to be a 2. The second root or the square root. Rather than writing it out all the time with the 2 there, mathematicians decided to save time and just agree that when there's no little number in the V, we're talking about the square root or the second root of a number. So I wrote it with the 2 here, but you'll never see it that way. I just wanted to make this point, as you'll see in a moment when I get on to some of the other roots. And this is always how roots work. When you see the square root of 49, you're being asked, what number can I square to get 49? And 7 squared is 49, so the square root or second root of 49 is 7. And the square root of 144 is 12, because 12 squared is 144. And the square root of 900 is 30, because 30 squared is 900. Now, I want to take a very brief look at some other roots. This is the only page here where we're going to deal with roots other than square roots. The rest of the way, we're going to confine ourselves to square roots. But I just wanted to review for you because I think I've taught you this already. Here we have a little 3 in the V. These little numbers in here are called the indices, or one of them is an index. That's not a very important vocabulary word, but it does have a name. So we've got the third root, which is also known as the cube root, the fourth root, the fifth root, and the sixth root. And you can have any whole number 2 or above as the index in that little V. And of course, when it's a 2, we don't write it there. We assume that it's a 2. Now, the cube root of 64 is 4 because 4 cubed is 64. See, so you take the 4 here, which is the answer, and you put this exponent on it of 3, and you get the number inside. The fourth root of 16 is 2. Why? Because this 2 raised to the fourth power is the number inside. The fifth root of 100,000, notice 100,000 has 5 zeros. The fifth root of 100,000 is 10. Why? Because 10 raised to the fifth power is the 100,000. And finally, this is one that I didn't know. I looked it up. I worked it out. I wouldn't expect you to know this, but the sixth root of 729 is 3. Why? Because 3 raised to the sixth power is 729. And why don't you check that out for yourself? I think that would be a good thing to do. Let me use a little bit different way of articulating this idea of what a root is. When you see this square root of 49 symbol, you're being asked the question, what can I raise to the 2 power to get 49? What can I multiply by itself to get 49? The square root of 144 is asking you the question, what can I raise to the 2nd power to get 144? And the square root of 900, what can I square? What can I multiply by itself to get 900? With these others here, this little symbol here, the cube root or the 3rd root of 64, is asking you the question, what number can I raise to the 3rd power to get 624? What number can I multiply 3 of them together to get 64? And that number is 4. That's why it's the cube root of 64. It's a really simple concept. Roots are the opposite operation of exponents, if you want to look at it that way, sort of reverses the thinking process on exponents. When you see the 4th root of 16, you're being asked the question, what number can I raise to the 4th power to get 16? What number can I multiply 4 of? 2 times 2 times 2 times 2 is 16. So the 4th root of 16 is 2. This is asking the 5th root of 100,000. What number can I raise to the 5th power to get 100,000? And the answer is 10. And this last one is asking, what number can I multiply 6 of, or what number can I raise to the 6th power to get 729? And that's why the 6th root of 729 is 3, because 3 to the 6th is 729. Please always remember that definition of roots. What question is being asked? That's very important to master now. So the rest of the way we'll focus on just square roots. And so you won't see any number in the V here. You won't see any index indicated. So we assume that it's a 2 or a square root. So let's just agree that the square root of 36 is 6 and the square root of 49 is 7. Right? Pretty straightforward. But what about all the whole numbers between 36 and 49? What about the square root of 37, the square root of 38, the square root of 39, and so on, all the way up to the square root of 48? Well, what I want you to realize, I cannot prove this to you, not because it's beyond Algebra 1, but because it's beyond me. This is some pretty sophisticated math that I think might have been done in the 19th century. But it's very involved, but there are certain things in math that are beyond us, but we just have to trust the mathematicians when they say that it has been proven. What has been proven is that all of these are irrational. If you have the square root of a whole number, and that square root is not a whole number, then the square root is not a fraction. The square root of 37, for example, cannot be represented as a fraction. In decimal form, the decimal digits would go on forever without repeating. That's another way to define an irrational number. An irrational number is a number that cannot be represented as a fraction or a negative fraction. And from the decimal point of view, the digits go on forever with no repeating. You can never put a bar over any digits if you have an irrational number. Now, calculators can approximate for us. I used a calculator, and the calculator told me that the square root of 37 was approximately, notice the squiggly equal sign, 6.08. The calculator actually gave me many more digits than that. I just rounded off to the nearest hundredth. And the square root of 48 is approximately 6.93. If you multiply 6.08 by itself, you're not going to get 37, but you'll get close to it. All of these square roots over here, their representations on the calculator will begin 6 point something. They have to, because all of these are going to be bigger than 6, right? The square root of 36 is 6. So the square root of all of these, square root of 37, square root of 38, all the way up to the square root of 48, have to begin 6 point something, because they're between 6 and 7. But what I want you to realize is that they are irrational. It's impossible to represent them as fractions. Well, now we move on to, ladies and gentlemen, the real focus of this video, which is simplifying a root. And I want to start with one that's about as simple as you can get, and as easy as you can work with for this skill. The square root of 20. Now, the square root of 20 is irrational. If you type into a calculator 20, hit the square root key, you're going to get 4 point and then a bunch of digits. And actually, I did that, and I rounded off to the nearest hundredth. The square root of 20 is approximately, this is the squiggly equal sign, approximately 4.47. But that's really not what we want to do. That's not what the skill is, getting an approximation with the calculator. The skill works like this. You can think of the square root of 20 as the square root of 4 times 5. Now, I want to make this point. You could obviously represent 20 as 2 times 10. But that's not helpful here. The best way to think of the 20 in terms of factorization is 4 times 5. So I've written the square root of 4 times 5, which is obviously the same as the square root of 20. The rule tells us that what we can do is break this apart. The square root of 4 times 5 is always going to be the same as the square root of 4 times the square root of 5. You can put this in words the following way. It's a little bit wordy. It's much better to look at it symbolically, which I'm going to do for you in a little bit. But what the rule says is that the square root of a product is the same as the product of the square roots. See if you can understand that way of putting it into words. The square root of the product of 4 and 5 is equal to the product of the square root of 4 and the square root of 5. Now, the square root of 4 is 2, the whole number 2. So we can substitute the whole number 2 for the square root of 4 right here, and then times the square root of 5. This is not an approximation. 2 times the square root of 5 is exactly equal to the square root of 20. And as I wrote down here, it's still irrational. We have not somehow magically changed the square root of 20 into a rational number, into a fraction. It is not. It is still irrational, because if you take the irrational number, the square root of 5, the square root of 5 is irrational, and you multiply it by the whole number 2, that result is irrational. Okay? Now, let's take a look at, we're going to take a look at why this is true. Why the square root of 20 is equal to 2 times the square root of 5. This is the skill. This is the skill that you need to learn during this video. But before we look at why it's true, we need to introduce a definition. The square root of a times the square root of a is a. And I wrote that 2 ways. This up here, the square root of a squared, is, of course, the square root of a times the square root of a. Either way you write it, the result is a. Now, why is it? Why is the square root of a times the square root of a? Because that's the definition of square root. Remember I said before, what does it mean to say, what is the square root of a? Well, the square root of a is the number which, when you multiply it by itself, you get a. Right? Let that sink in. Make sure you understand that. The square root of a number is the number which, when you multiply it by itself, you get the number. The square root of a is the number which, when you multiply it by itself, which we did here, you get a. So there's really nothing to work out there. That's the definition. That's what a square root means. I put a question mark on the equal sign until we get down to the very bottom. The very bottom is 20 equals 4 times 5. I think we can assume that that's true. Eventually, we're going to get to the fact that 20 equals 4 times 5, which, of course, is true. So all of these question marks here, we can, when we're done going through this, we can eliminate them, because it is true that the square root of 20 is equal to 2 times the square root of 5. But let's see why. Let's square each side. Now remember, one of the fundamental things about solving equations, we're really not solving an equation here, but if you do the same thing to both sides of an equation, you keep the equation balanced. And here we're squaring both sides. If you square the square root of 20, as I just showed you on the other page, remember, the square root of a times the square root of a is a. So the square root of 20 times the square root of 20 is 20. If you square the square root of 20, you get 20. Now over on the right side, we have 2 times the square root of 5. We're trying to prove that 2 times the square root of 5 is the same as the square root of 20. Well, we're going to square 2 times the square root of 5 as well, just like we squared the square root of 20. If we square 2 times the square root of 5, we have 2 times the square root of 5 times 2 times the square root of 5. That's what it means to square 2 times the square root of 5. 2 times the square root of 5 times 2 times the square root of 5. The associative and commutative properties allow us to rearrange, regroup numbers any way we want when we're multiplying. So let's think of it as 2 times 2 times the square root of 5 times the square root of 5. Right? Just take the 4 numbers that are being multiplied and rearrange them. 2 times 2 is 4. And what is the square root of 5 times the square root of 5? It's 5, by definition. So we're done. We have shown that the square root of 20 is exactly equal to 2 times the square root of 5. Because when you square either one of them, you get 20. So they must be equal. I just want to point out a bit of an issue that some of you might have, some of my students have had in the past. You might say to me, hey, Mr. LaBeouf, I thought you told us that the square root of 5 is irrational, so the decimal digits go on forever without repeating. So how can it be that when we multiply the square root of 5 times the square root of 5, we get 5? Well, let's say that you take the result of a calculator for an approximation of the square root of 5. Let's say you go to 5, 6 digits. Of course, it would start 2 point, and then whatever the calculator tells you. And then you go ahead and multiply that by itself. Maybe you do it manually, because if you do it by the calculator, it might round it to 5 and tell you the answer is 5. But of course it wouldn't be, right? You know, whatever that last digit, you're not going to get exactly 5. Just think about multiplying 2 point and then a bunch of digits times itself. There's no way that's going to come out to exactly 5. But it will probably come out to something like 4.999998 or something like that. It'll come out extremely close to 5. And the more digits you use from the calculator approximation, the closer you'll get to 5. But that doesn't change the fact that if you did that decimal calculation, you wouldn't get exactly 5. That does not change the fact that the square root of 5 times the square root of 5 is 5. Because this number, even though it's irrational, the square root of 5 is the number which, by definition, when you multiply it by itself, you get 5. So you don't have to worry about decimal calculation. The definition of square root guarantees that these two numbers here, even though they're irrational, multiply to 5. What we have here is the general proof that the square root of a times b is equal to the square root of a times the square root of b. It doesn't work for just the square root of 20 and being this and the square root of 4 times 5, the square root of 4 times the square root of 5. It works for any a's and b's. And again, let me put this into words again. The square root of a product, the product of a and b, the square root of a product is equal to the product of the two square roots. You break it apart like that, right? Well, let's prove it, and the proof is just like the other one, right? If you square the square root of ab, the square root of ab times the square root of ab is ab by definition, right? And now let's square the square root of a times the square root of b. Well, that would be the square root of a times the square root of b times the square root of a times the square root of b. We reorder and regroup so that we do the square root of a times the square root of a, which is a by definition, and the square root of b times the square root of b, which is b by definition. So because we square both of these and get the same result ab, they must be equal. This is a proof of this law of math with the roots. Okay? This is the key. This is the key to simplifying a root. And by the way, I think I neglected to say something earlier when I was doing the square root of 20. The square root of 20, in order to simplify that, I thought of the square root of 20 as the square root of 4 times 5. I think I mentioned, why not 2 times 10? Well, the thing about that is, let me just squeeze it onto this title paper here. If you think of the square root of 20 as the square root of 2 times 10, now that's a true statement, obviously. The square root of 20 is the square root of 2 times 10. But then if you break that apart, the law tells us that the square root of 2 times 10 is the square root of 2 times the square root of 10. That's not terribly helpful, though, because neither one of these is a whole number. The square root of 2 is irrational. The square root of 10 is irrational. Now, you can actually keep going and get to the eventual result. The best way, the quickest way to do the square root of 20 is to think of it as the square root of 4 times 5. The square root of 2 times the square root of 10, the thing is, it's extra work. It's an extra step. What you would have to do here is continue working with the square root of 10 until and represent it as the square root of 2 times the square root of 5. And then you can combine these two square roots of 2 to get 2, and there you have the same result, that the square root of 20 is 2 times the square root of 5. But it took an extra step to get there if you choose 2 times 10. So what you want to do is, you want to, when you're trying to simplify a root, you want to think of factors of that number that are perfect squares. You want to come up with a factor of the number in here that's a perfect square. And the one that I used earlier was 4. Okay. We'll see more of that as we go on. The next one I want to do with you, you'll see an example of what I just said right here. I want to consider the square root of 75. The square root of 75 is irrational. 75 is not a perfect square. The square root of 75 is not a whole number and is not a fraction either, but we can simplify it. You have to think of factors of 75. Now, in this case, probably the first two factors that are going to occur to you for 75 are 3 times 25, most likely. 5 times 15 is also 75, but the one that works here is 75 is 25 times 3. 25 is a perfect square. So we represent the square root of 75 as the square root of 25 times 3. Then the rule tells us we can break that apart into the square root of 25 times the square root of 3. And the square root of 25 is the whole number 5. So we're done. The square root of 75 is exactly equal to 5 times the square root of 3. Either way you represent it, it's irrational. Okay, let's prove why. Let's square the square root of 75. Well, when you square the square root of 75, by definition, you get 75. The square root of 75 times the square root of 75 is 75 by definition. And then we're claiming that it's equal to 5 times the square root of 3. So let's square that over here. Squaring 5 times the square root of 3, we get 5 times the square root of 3 times 5 times the square root of 3. We rearrange the 4 numbers to 5 times 5 times the square root of 3 times the square root of 3. 5 times 5 is 25. And the square root of 3 times the square root of 3 is 3. 25 times 3 is 75. So we have proven that the square root of 75 is exactly the same as 5 times the square root of 3. This is the skill. Along with the square root of 20 was the first example, the square root of 20 being 2 times the square root of 5. This is the second one. The square root of 75 is exactly the same as 5 times the square root of 3. Let's consider the square root of 80. And I intentionally did something here to make a point. Remember I said that you need to think of factors of the number that are perfect squares. Well, 4 is a perfect square, and 4 times 20 is 80. So we can think of the square root of 80 as the square root of 4 times 20. Break this apart. The law says that this is equal to the square root of 4 times the square root of 20. The square root of 4 is 2. So the square root of 80 is 2 times the square root of 20. And we're done, right? We've simplified the square root of 80. So we're done. Not quite. We've simplified it, yes, but we've not simplified it fully. Remember when you were first learning to simplify or reduce fractions, right? Let's say you had 12/18ths, and you wrote that 12/18ths is equal to 6/9. That's a true statement, but we have this expectation and rule that we simplify fractions fully. So what the teacher's really looking to get out of you here is that 12/18ths is 2/3. Now it's fully simplified. Well, there's a very comparable thing that goes on with simplifying a root. We already know the square root of 20 can be simplified. We already did it. I chose it that way on purpose. I don't have to reinvent the wheel, don't have to redo the work. We already know that this is 2 times the square root of 5. So we have the 2 that we already got times 2 times the square root of 5, right? The first thing we did was the square root of 80 was equal to 2 times the square root of 20. So that 2 is part of the answer. But the square root of 20 itself is 2 times the square root of 5. And then we do 2 times 2 here to get 4. 4 times the square root of 5. That's the final simplified result for the square root of 80. It's kind of like the 2/3 over here. It's fully simplified. Now, whenever you get to the simplified root in multi-steps like this, there were really 2 steps here. I went to 2 times the square root of 20, and then I went to the final answer of 4 times the square root of 5. You can always look back and say, was there a bigger factor of 80 that is a perfect square? And if you look at this 4 here and you think about it for a minute, this 4 in the final answer, doesn't that mean that 16 has to be a factor of 80? If you didn't get to that on your own, if you don't see what I'm talking about, let me go through this. It is true that 80 is 16 times 5. It's not something that may be right there at the tip of your tongue because we don't generally study multiplication facts up to 16. But 16 times 5 is 80. 16 is a perfect square. So we can go from this to the final result. So a question that many of you would ask right now, do I have to do it in one step? The answer is no. Very often I don't do them in one step because I don't recognize the biggest factor of the number that is a perfect square. You don't have to do that, but if you don't happen to choose the one-step method, you have to keep going. All right. How about this one here? This is a cute one. The square root of 256. Let's say that's presented to you and you're asked to simplify it. Well, would you recognize that 4 is a factor of 256? Well, maybe you'd have to think about it for a moment, but it is. 256 is divisible by 4. 4 times 64 is 256. So let's say you realize that 256 is 4 times 64. So you went down that road. You break this apart into the square root of 4 times the square root of 64. And look what happens this time. You get 2 times 8. The square root of 4 is 2. The square root of 64 is 8. 2 times 8, 16. So the square root of 256 is not irrational because it's 16. Now, let me show you a little something here. I wrote down at the bottom, see the n squared table. See that? See the n squared chart? I wrote that down here to remind myself to go back and show you. Pretty clever on my part. You see how I stopped at 15 here and then I skipped to 20? Well, if I had put 16 here, then 16 squared is 256. Will you memorize? Will you know that the square root of 256 is 16? Is that something you'll memorize? Maybe, maybe not. But if you tried to simplify it, if you tried to simplify it, you would get to that result. So that can happen sometimes when you simplify a root. It might end up being a whole number because you didn't recognize that that number inside was a perfect square. How about this? The square root of 30. Okay, now that's irrational. 30 is not a perfect square. The square root of 30 is somewhere between 5 and 6, and it's irrational. The calculator could give you a nice approximation, 5 point whatever. All right, let's try to simplify it. Let's think of it as 5 times 6. The square root of 30 is the square root of 5 times the square root of 6. That's true, right? Right here. But is it simplified? Well, these are both irrational. Is it simpler to express the square root of 30 as the square root of 5 times the square root of 6? The answer is no. Well, maybe we didn't go far enough. Well, how about the square root of 6? That's the square root of 2 times 3. Or the square root of 2 times the square root of 3. So no matter what we do here, even if we'd started with the square root of 3 times the square root of 10, we'd get the same result. The point here is that the square root of 30 cannot be simplified. Do not express it as the square root of 5 times the square root of 6, or the square root of 3 times the square root of 10, or the square root of 2 times the square root of 5 times the square root of 3, like this. Don't do that, because it's not simpler. It's more complex. Not all roots can be simplified. Okay? Now you might want, well, wait a minute, 30 is not prime. It should be clear to you that the square root of a prime number cannot be simplified, right? The square root of 41 or the square root of 17. Obviously, those cannot be simplified because they have no factors other than 1 in themselves, right? Well, 30 is not prime, but the thing is, 30 does not have any factors that are perfect squares. 4, for example, is not a factor of 30. 4 is a perfect square, but it's not a factor of 30. That's why it couldn't be simplified. You might legitimately raise the question, why simplify? Well, I can tell you that when we get to chapter 8 of our textbook, it's going to be essential that we can simplify a root in order to show that 2 different ways of solving a problem from chapter 8 can only be shown to be the same result if we can simplify a root. It's going to be an important skill when we get to chapter 8 for reasons I can't get into right now. But here's another reason why we might simplify a root. Assume that you know that the square root of 5 is approximately 2.236. So you know that. And now you're faced with the square root of 8,000, and you don't have a calculator. When I was taking Algebra 1, I'm pretty sure calculators that could give you square roots existed, but not many of us had one because they cost over $100. Now, nowadays, the graphing calculators cost over $100. But what I'm talking about is the basic calculator that adds, subtract, multiply, divide with whole numbers or decimals, and the square root key. The cheapest calculator that we have today cost over $100 back in the early 1970s when I was taking Algebra 1. So not many of us had them. But what we might have, we did have in the back of our textbook was a table of square root approximations. You could look in the back of the book and find that the square root of 5 was approximately equal to 2.236. But the table wouldn't go up to 8,000. It wouldn't give you an approximation for the square root of 8,000. So simplify the square root of 8,000. And I'm going to just take a shortcut. I chose 8,000 because I knew that it was 1,600 times 5. 1,600 is a perfect square. You should recognize that. So we can break apart the square root of 1,600 times 5 to the square root of 1,600 times the square root of 5. And what's the square root of 1,600? 40. So if you need an approximation for the square root of 8,000, you don't have a calculator, and you know that the square root of 5 is this, just multiply it by 40. That's easy. Even without a calculator, it's very easy to multiply 2.236 by 40, and that will be an approximation for the square root of 8,000. So this answers the question, why simplify? It used to be a very practical skill before calculators. And ladies and gentlemen, let me see. I noticed that we're up over 35 minutes. I actually have some other papers here that, yeah, I'm going to skip a few that I had planned because they're kind of like, it's summer. It takes things a little bit too complex than we need to get to. Let's finish off, however, with some examples. Some examples that you should be able to do. All right? You should be able to simplify these roots. Let's take the square root of 112. The square root of 112. Well, I think it's easy to recognize that 4 is a factor of 112, isn't it? So think of it as the square root of 4 times 28. Why 28? Well, 112 divided by 4 is 28. Okay? So now we have this, we can break this apart to the square root of 4 times the square root of 28. The square root of 4 is 2, so we have 2 times the square root of 28. Ask yourself, am I done? Or can I simplify more? Well, 4 is also a factor of 28. So we've got the 2. That 2 has to stay there as part of our answer. There's 2 out here, okay? 2 times the square root of 4 times 7. 2 times the square root of 4 times the square root of 7. This square root of 4 is 2. So we get 2 times the square root of 7, or 4 times the square root of 7. At this point, once you get to that result, that the square root of 112 is 4 times the square root of 7, you might have said, well, could I have done this in one step? Well, look at the 4. The fact that this whole number 4 is part of our simplified root means that 16, 4 squared, must be a factor of 112. And it is. We probably wouldn't recognize it right off the bat, but the square root of 112 is the square root of 16 times 7. 16 times 7 is 112. Break it apart. Square root of 16 times the square root of 7. Square root of 16 is 4. There's the answer in one step. Do you have to do it in one step? No. But when you got to this point, 2 times the square root of 28, you have to finish. Okay? So the square root of 112. Maybe you should, on a piece of paper, not look at this, pause the video, not look at this, and go through the steps of simplifying the square root of 112. How about this one? The square root of 6750. Now, the ones I ask you to do, or the ones that any textbook authors would ask you to do, are going to be reasonable. You might look at this and say, wow, that's a big number. How am I going to do that? You got to have faith in the person giving you the problem that it's going to be something reasonable that you can do. Doesn't mean it'll be easy and you'll get it immediately, but it'll be reasonable. Any number that ends in 50 has 25 as a factor, right? Isn't it obvious that 25 is a factor of 6750? 25 is a perfect square. So if you're trying to simplify a root and you can look at it and say, hey, 25 is a factor of that number inside, that's a good place to start. So the square root of 6750 is the square root of 25 times 270. Now, where did I get the 270? 6750 divided by 25, of course, right? Break this apart to the square root of 25 times the square root of 270. Square root of 25 is 5. So the square root of 6750 is 5 times the square root of 270. And we're done, right? No, because 270 has a factor that is a perfect square. And it's pretty easy to recognize that, isn't it? Isn't 9 a factor of 270? So this is what you have to do when you're simplifying roots. You have to look at the number inside and ask yourself, is there a perfect square? Is there a perfect square that is a factor of that number? Or said the other way, does that number have any factors that are perfect squares? And if you can identify one, you can get started. And Don't worry about if it's the best, quickest way to do it. Just get started and see where it heads. So we've already got a 5 outside, and then we have the square root of 270. Think of that as the square root of 9 times 30. Why 9? Because 9 is a perfect square. Break this apart. So we've got the original 5 times the square root of 9 times the square root of 30. This gets broken apart to this. That's the rule that will always work. And the square root of 9 is 3. So we have 5 times 3 times the square root of 30. 5 times 3 is 15. The final answer here is 15 times the square root of 30. And we already talked about the fact that the square root of 30 cannot be simplified. So we're done. In hindsight, however, okay, now this is definitely something I wouldn't expect you to do, and I very much doubt that I would have done it myself. 15 squared is 225. Now, I kind of know that, but I wouldn't have necessarily thought of it in this problem. So I probably, if I were taking an Algebra 1 test and I were presented with this, I would probably do it just the way I did on this paper. But you see, we ended up with the 15 out here. Okay, the whole number 15. So that means that 15 squared must be a factor of the 6750. Make sure you can understand why that's true. All right, 15 squared is 225. And if you do 6750 divided by 225, you'll get 30. 225 times 30 is 6750. So if you were just brilliant and you said, oh, 225 is a factor of this and it's a perfect square, you could have done it in one step. But it's unlikely that anyone would do that. Okay, 1, 2, 3, 4, 5 more examples. We're up to about 42 minutes. We should be done in just a little bit more than one class period of 45 minutes. We may go up to 50 minutes or so. I'll try to go through these fairly quickly. And notice I threw in one here. Let's look at the fourth one down here. Maybe this wasn't the best choice for me because the square root of 3600, you're asked to simplify that. Isn't it obvious that it's 60? I should have chosen something that wasn't quite so obvious. But let's say you didn't recognize that the square root of 3600 is 60 and you tried to simplify it. Well, you might say, oh, 100 is a factor. 36 times 100. So you say, okay, this is the square root of 36 times 100. Break it apart. Square root of 36 times the square root of 100. Well, the square root of 36 is 6. The square root of 100 is 10. 6 times 10 is the 60. So sometimes if you don't recognize that the square root of a whole number is also a whole number, and you start to try to simplify it, you end up realizing that it's a whole number. You look back and say, oh, of course, right, of course it's 60. So that's the fourth one here. Let's go back and do the others. The others are not going to turn out to be whole numbers. The square root of 52. Well, I think you should know that 4 is a factor of 52. A standard deck of playing cards has 52 cards, 4 suits, 13 in each suit. 4 times 13 is 52. So break it apart. Think of the 52 as the square root of 4 times the square root of 13. Break it apart. Square root of 4 times the square root of 13. Square root of 4 is 2. 2 times the square root of 13 is the square root of 52, which, by the way, again, let me repeat, they're both irrational. No matter which way you represent the number, square root of 52 or 2 times the square root of 13. Either way, it's irrational. And on the calculator, it would be 7 point, and then a bunch of digits for an approximation, right? Square root of 52 is a little bit more than 7, right? Irrational. The square root of 2,000. Here, I don't think it's too much to expect that you realize that 400 is the biggest factor of 2,000 that is a perfect square. Now, the biggest factor of 2,000 other than 2,000 is 1,000. 2 times 1,000, right? But 1,000 is not a perfect square. It's got 3 zeros. In order for a power of 10 to be a perfect square, it has to have an even number of zeros, right? But anyway, 400 is a perfect square. So think of the 2,000 as 400 times 5. The square root of 400 times 5 is the square root of 400 times the square root of 5. The square root of 400 is 20. So the square root of 2,000 is 20 times the square root of 5. The next one is the square root of 96. The square root of 96. Well, once again, 4 is a factor. 4 is a factor of 96. It's 4 away from 100, right? 4 is obviously a factor of 100. 96 is 4 less, so 4 is a factor of 96. So think of the 96 as you know what? 4 is a factor of 96, but I did it a shorter way. Why don't you try this? Why don't you try to simplify the square root of 96, starting out as the square root of 4 times 24, right? 4 times 24 is 96. So work it out as the square root of 4 times 24 and keep going till you're done. You're going to get the same result I did. But 16 is also a factor of 96. I knew that when I wrote it on paper. I forgot just now. All right. 6 times 16 is 96. Do you need to really know that? No. But it's helpful here, right? So think of the square root of 96 as the square root of 16 times 6. Break it apart into the square root of 16 times the square root of 6. Square root of 16 is 4. So the square root of 96 is 4 times the square root of 6. And if you started out as the square root of 96 being the square root of 4 times 24, you would have gotten to the same result if you kept going. And the last one down here, the square root of 490. This is actually a very simple one. Many of these after a short time, you'll be able to do mentally. This one right here is pretty easy to do mentally, right? Because 49 is jumping out at you as a factor of 490. 49 is obviously a factor of 490, and 49 is a perfect square. So think of the 490 as 49 times 10, the square root of 49 times 10. Break it apart. Square root of 49 times the square root of 10. Square root of 49 is 7. So the square root of 490 is 7 times the square root of 10. Ladies and gentlemen, it's been a pleasure to address you through these YouTube videos during the summer, and it's been a variety. I remember the very first thing we did was that legendary story about young Gauss, who was able to almost instantly come up with the sum of the first 100 natural numbers. That was a more sophisticated topic than what I just presented to you. It was more interesting. Harder, maybe, if you want to put it that way. Maybe I should have started with the easy thing first, but I wanted to start with something that was dramatic. And I actually have begun Algebra 1 classes in the past in late August or early September with the story of young Gauss in the classroom. And so I thought that would be a good thing to do with these summer videos. This one here, you know, very, very mechanical, very straightforward, that you will, like anything else, become good at through practice. So I'm going to provide you with a sheet that I would like you to do, simplifying roots, like some of the ones that I did here. And it is a skill that you will use not only this upcoming school year during Algebra 1, but you will continue to be expected to be able to do that by your high school teachers. And it's a very mechanical skill. So, like I said, it's been a pleasure. As I record this, it's Monday, August 3rd, I think. So we're going to be back together soon. I look forward to that. I hope you enjoy the remaining days of your summer, and email me if you have any questions. Take care, folks. See you soon.